Supplemental math videos from Circle Christian School. Okay, kiddos, it's time to solve trig equations. You've done them before. Everything's really basically the same. You just have to look for the best way to go find the x in here. It's all about inverses to begin with. And sometimes we just have to kind of mix things up a little bit to get to that inverse. All right, basically this is what happens when you try to solve anything for x. You got to just do the basic isolating of the variable. With these, you have to just kind of see if there's not something that you can factor. Can it be set to 0? Does it look quadratic? 3, do you need to change something so that you have some common trig? And number 4, the interval range can be determined by checking the parent graphs out located in the back cover of your book. That's where the intervals come from, Drew. All right, I know these are ones that we did in the book, but sometimes it's just kind of helpful to have a little bit of voice back behind it again. Same thing. I'm still not really doing anything different from what I am kind of used to doing. Got my little fence of equality here. We have to move things back and forth. We got to get the trig all by itself. There we go. And that means we're just going to add 1 to both sides. And that's going to leave us with the 2 sine x, which of course equals a positive 1. Then we're going to divide out the 2, the most basic ones that are in here. Those are the ones that we love. And we end up with x equaling 1/2. Well, what does that mean? X equals 1/2. Does it really equal 1/2? Well, no, what we have to do is look at what sine means at 1/2. And taking a look at our handy dandy chart, we notice that sine 1/2 means pi over 6 and 5 pi over 6. And you can take a look at the picture of the book as to why they qualify it with the fact that we've got sine in movement here, and why you have to have that 2n pi happening, the plus and the minus. It's all about a little bit of manipulation. We notice that here, if we get everything to kind of be in cotangent, we can play with it. So we're just going to jump the fence over here so that we can have cotangent x, cosine squared x, equals. I don't want equals. I wanted minus. I'm so glad we've got white out here. Okay, and minus the 2 cotangent x. We're just going to set everything to 0 because that's going to allow us for some factoring. We're going to be able to factor out the cotangent x. So we have cotangent x, which leaves us with the cosine x minus the 2 equals the 0 now. Okay, so that leaves us with 2 factors here that we are going to set to 0 so we can go and solve. So we have cotangent x equals 0, which means the x is going to equal 0. And we have cosine squared x minus 2 equals the 0. So we're going to add 0 to both sides. So we have the cosine squared equals 2. We square root both sides. And so we have cosine x equals plus minus the square root 2. Taking a look at our sheet, we notice that for cotangent, that x has 2 values to it. One value to it, which is the pi over 2. But there is no readily available solution for cosine at square root 2. So it's just somewhat extraneous. All right, in this one, we have to figure out if we want to deal with sine or if we want to deal with cosine. Remembering that sine squared x is the same thing as 1 minus cosine squared x, gives us that advantage of being able to have some cosine stuff going on. Oops. Okay, it's an x. Who knows why silly little things do what they do? Let's distribute this guy out. So we end up with a 2 and a minus 2 cosine squared x plus a 3 cosine x. Let's see if it acts better this time. It did. Minus a 3. So we're going to combine these like terms right here. And that gives us a negative 2 cosine squared x plus the 3 cosine x minus the 1. And again, we got to kind of look and see, hey, can it be factored? Does it look quadratic? Yes, it does. Very good. So I am actually going to get rid of the negative outside here to do this. And that's going to give me a 2 cosine squared x minus the 3 cosine x plus the 1. And sometimes now it's just a little bit easier to make it look quadratic at this point. So what do we have? We have a negative 2x squared minus a 3x plus the 1. Okay, I know I'm going to end up with a double bubble, but I don't want to lose that little negative inside there. Factor by grouping, so I need factors for 2 that give me a negative 3. So negative 2x and a negative 1x plus a 1 and the 2x squared. So I'm just going to do some factor by grouping here. Let's see if I can define my groups without getting too squishy. All right, take out the 2x. It's going to give me x minus 1. Minus, going to take out the 1. Has to be x minus 1. All right, very good. Now we can take a look at this, and we have 2x minus 1, and we have x minus 1, which means x is going to equal a positive 1/2, and x is going to equal 1. And we go and take a look at our handy dandy little sheet for cosine. This is going to be cosine 1/2 and cosine 1. And that means that cosine at 1 equals 0. And cosine 1/2 equals pi over 3. And 5 pi over 3. You okay? All right, another one is where the x is a little bit challenging here. We have 3 tan x over 2 plus a 3. I've already done the work for you. In general, we find out that tan x over 2 equals negative 1. Looking at the paper, the negative 1 equals the 3 pi over 4. So what we're left with in turn here is that tan x over 2 equals the 3 pi over the 4. Now there's a whole bunch of nonsense there that we've got our little interval going on here. So yes, technically we can have the number, of pi's or revolutions technically happening here. So we can add that, but the problem is, what are we going to do with the 2? So what we're just going to do to get rid of the 2 so that we end up with just tan x is, you guessed it, we're going to multiply both sides by a 2, which in turn means we have to multiply both of these by a 2, which gives us a 6 over 4 pi, which is the same thing as 3 over 2 pi. And technically, since we can have so many little revolutions, it'd just be 2 times the number of revolutions, pi. Okay, using inverse functions, we let's say, for instance, we're looking more for the angle or the arc, sine, arc, cosine, arc, tangent value of a trig function. It's really kind of just about the same game. It's just that we have these restrictions that happen with our inverse functions, the little intervals or the range. And as I said before, you can easily find those by locating the graphs in the back cover of your book. They have all the domain and the range and so forth and so on. Inverse functions, you'll remember, for it to be one-to-one is that we have to restrict the area depending on whether it's sine, cosine, or tangent. And again, if you need to, you can go back to chapter 4, take a look at the inverse functions and the parents and a little bit of an explanation about that. It's just that we have a certain area that we're talking about. Okay, so that's going to give us a tan squared x minus the 2 tan x minus the 3 equals 0. Nice little doubly bubbly going on here. There we go. I'm just going to make it look a little more quadratic and play with it that way instead. So this is going to be an x and this is going to be an x. We got the 3, the 1, the big number carries the sign here, and equals the 0. So we have that tan x basically is going to equal the 3, and tan x will equal a, my bad, here we go, that's a plus sign. I knew it was something different there. -1. And looking at the paper, you'll see that there's not anything for 3, but it's just going to be that many times. You know, it's just an arctangent 3. And then for the -1, you have to remember the restrictions here, looking at the paper, that all the -1s are something that are greater than pi over 2, or the negative pi over 2. So we actually have to use the part of the restriction, which is the positive one. And that's going to be negative pi over, well, it's going to be pi over 4, but because it's a negative pi over 4. And that's because of the restrictions up top here. Okay, we're going to find the surface area of a honeycomb, or examine the surface area of a honeycomb. Personally, I'm trying to figure out what kind of people would do that and why. So I'll leave that to you to go and Google. I thought I was doing pretty good to hand draw the picture of the honeycomb here. So we're going to use a little bit more of the calculator in trying to find the answer for this. So we're basically going to jump the 12 over here so that we have everything equaling 0. So 8, 4, 3, 7, 5. The square root of 3 minus the cosine theta, which we can actually just call x, over sine x, and minus the 1.2, because that's the result of combining the two. put the function into your graphing calculator, and you get a shape like so. And we're just going to use the root feature to go find the two values right here. First one right here, make sure your calculator is in degree mode because we're actually looking for the angle on this one, so it has to be in degree mode. The first one results in approximately being 54.7 degrees, and oh, now I'm stuck. Hold on a sec. Okay, that was a bit of a baby break, so I ended up losing my train of thought here. So let me white this out really quick. If I do a big whiteout, it's a lot quicker. There we go. Okay, so the first one is approximates at about 49.9 degrees, and the next one is at about 59.9 degrees here, and so those are our roots, and so that is the surface area when we have 12 square inches. And the next one is what is the minimum, and the minimum is just going to be the base equation to begin with. So it is the 10.8 plus the rest of it there with the surface area, and you graph that, and again you find when y equals that, what is x, work a little bit on your you can use your minimum function there, and it's just the minimum point, do that little Tracy thing, you know, with the minimum gibber between here, left bound, right bound, minimum kind of stuff. And okay, and when you use the minimum feature in the calculator there, then the most minimum place you find after all the guessing is about 54.7. Okay, let me tell you what's really important about this is, oh my gosh, how do I get this thing into my calculator? So let me get some stuff out of the way here so I can show you a little bit of calculator stuff, because you got to be real careful with a lot of the parentheses inside here to get it to really kind of play. Also, you can look at your book. It'll pretty much show you how to settle this out. But when I put it in my calculator, for it to really kind of work good, I put in, excuse me, the 10.8. Oh, forgot I got the big guy on. Okay, 10.8 plus the 0.84375. Oh, can't look at the calculator and write at the same time. But the big thing here is I had to put parentheses, parentheses, and parentheses, which of course my calculator has neat little parentheses going on for my radical here, minus cosine, parentheses x, parentheses divided by parentheses the sine x, parentheses, 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 and I think I'm finally done with all my little parentheses. So not only am I trying to figure out why we need to know the surface area of a honeycomb, I'm also still trying to figure out why we couldn't come up with something that was a little bit easier to put into a graphing calculator. Go figure.